Swayam Prabha. Digital India. Educated India.
To you, right? So that's where I think I'm going to give you some ideas about the surface chemistry and surface chemical processes, which are very important. For example, if I take a chalk piece, you have any chalk piece here? There is a chalk. If you take a chalk piece here, it has a surface, cylindrical surface on this side and this side. Is this surface same as this? Physically it should be same, right? This is a termination here, this is a termination here, right? And then if you look into the bulk and then surface is same. No, bulk is different, surface is different. Which is more energetic, surface or bulk? Why? Why is that surfaces are more reactive or energetically more have a higher energy compared to bulk atoms? Okay, any other? See, the atoms which are sitting inside are fully satisfied in terms of bonding. They have coordination, for example, all coordinations are complete. They are bonded to neighboring atoms. Whereas the atoms which are sitting on the surface, one side they are not bonded, right? So, from bonding point of view, it is unsaturated, right? So, it is ready to interact with any molecules like from outside to get satisfied, so that the energy comes down, right? So, that is the reason why people make, for example, I just break this chalk piece, it is not breaking. I apply more force, oh, it's very difficult to break. So, what have I created now? I increase the surface area, right? So, I increase the surface area, I increase the energy, right? Because whatever I apply, the force applied is now hiding here as surface energy, right? So, I keep breaking it into smaller and smaller and smaller tiny particles. You are actually creating higher and more surface area, and then more and more energetic particles. Okay. So, surfaces are very important because energetically they are different, their reactivity is different, their atomic arrangements are different, right? And that is the reason why many processes take place on surfaces. We will look into some of those things, some of them probably a repetition for you, but it's interesting to see all that. Just before going to that, I just want to show you this interesting slide that life started 5000 years BC, before 5000 BC started the Stone Age, and then we came to Copper Age, and then we came to Bronze Age, right, and then we came to Iron Age, we came to Silicon Age, then to Carbon Age, now Atomic Molecular Age, Artificial Intelligence Age. How many of you are familiar with artificial intelligence? Artificial intelligence, Chat GPT. You are all already well aware of that. So, these artificial intelligence tools are also coming into chemistry now. Machine learning tools, artificial intelligence tools are coming into chemistry to predict the reactions, mechanisms, possible molecules that you can actually design, and then go and do the experiment in the lab, and so on and so forth, right. So, surface chemistry also will have a lot of influence from these artificial intelligence tools in the near future. Okay. Okay, coming back to surface chemistry, What is surface? What is interface? Right? So, surface, I have defined it here, surface is the shell of a macroscopic object. Example, inside of the material, in contact with its environment. There is a bulk here, a part of that is exposed to the environment. It can be liquid, solid liquid interface, liquid liquid interface, or solid gas interface, right. So, all these interfaces are basically, you can call it as a surface. So, interface is the boundary between two phases. If I have solid and liquid, I have an interface. That interface has different characteristics and different reactivity, right. Similarly, liquid liquid interfaces, for example, add water to oil. So, do they mix? There is interface there. That interface is different. That interface is different, right. Similarly, take a solid, expose it to gas, for example. So, there is a gas solid interface. That interface is different. Its reactivity is different, right. For example, lubrication. You take lubrication, you have this metallic pieces, you put some oil on that, put some oil, and then put another metallic piece and rub it. It slides very easily. Then put water. It is not that good, but right. So, in between two surfaces, there is an oil which forms an interface, right. So, when you put water, it is not that lubricant. It's not a very good lubricant. Water is not a very good lubricant, but oil is very good lubricant. What is the reason for that? When you think about at molecular level, what happens there? Oil is a long chain carbon chain, right? It could be C7, C8, C9, right? Whereas water is a small molecule. So, the hydrocarbon chain is little longer. So, it will not allow the surfaces to come in contact. So, they start sliding, right? Even take graphite, for example. Graphite and diamond, both are carbon materials, but the graphite, you can use it as a lubricant, because the two layers, they are separated by a certain distance because of the van der Waals forces, so they can slide over. Whereas the diamond is not possible, it is not possible to do that with the diamond, because diamond has covalent bond. Covalent bonds are much stronger, and it is a very hard material, right. So, the interfaces or surfaces, whatever you are talking about, is determines the physical and chemical properties, including stickiness, chemical reactivity, wetting, frictional behavior, and so on and so forth. And catalytic also. Catalysis is also one of them, right. Any catalyst, if you take, people don't use big chunks of metals. They make into smaller and smaller, finer particles and use it as a catalyst, because they increase the surface energy and the reactivity will be more. You can use more number of the catalytic particles for the to carry out the reaction. So, now, since the surface is very important, for example, these red balls that you are seeing are basically atoms on the surface. Bulk is not shown here. Now, here what happens is, you have a gas phase reactants. Reactants can be, the reactants come and adsorb on the surface. Something happens on the surface and then goes out as a gas phase products, right. If you add this gas phase reactants, two reactants together in the gas phase, they don't react, but you put them on a catalyst, immediately they will give you product. One example is, take hydrogen and oxygen, put it in a cylinder, in a flask, and leave it for some time. Will you get water? Will you get water or not? Hydrogen plus oxygen gives you water. Is that reaction possible? Not possible or possible? For a reaction to be possible, what is the thermodynamic criteria? Free energy should be negative, delta G should be negative. So H2 plus O2 gives you water is a thermodynamically feasible process, delta G is negative. But still these two molecules, if you put them together in a bulb, they don't react, they remain as it is. But the moment you put a catalyst, small speck of platinum, and then they will start reacting, they go and adsorb on the platinum and then start giving you water. So this is what is happening, the magic is on the surface, the magic is on the surface, right. So that's why the surface is called catalyst. So what would happen on the surface? So the molecules can go, for example, they can physically adsorb on the surface, they can have intermediates, right, and they can when the molecules adsorb, they can transfer the charge, and they can dissociate, and then they can diffuse from, suppose if the molecule is adsorbed, it can diffuse to other place, right, and then so on. All these things can happen. It can even take electrons from the surface, or it can give the electrons to the surface. All these things are possible on the surface, and some of these things influence the catalytic reactions. Okay. Of course, the surfaces will have vacancies. For example, there is one missing atom here, that is a vacancy. There is additional one atom which is sitting on top of that, that is the add atom. There is the edge here, there is the edge here. These are all surface defects. Right? If an atom is missing here, and then this part of the surface if you take, and this part of the surface if you take, which is more energetic, this one or this one? Vacant space is more reactive because it is missing there. So there is a unsaturation there. Whereas this atom which is surrounded by all these atoms is more stable, more comfortable, more stable, energetically more stable. Whereas this is not stable. Even this add atom which is sitting on the surface is not stable. Even these edge atoms are also not stable. The corner atom is also not stable. Not stable in the sense energetically they are not energetically favorable, right. So these are the places where all the reactions etc. can happen. On the surface, of course, surface is also not stable, is energetically not favorable. It is highly energetic. So things can happen on the surface. Okay, all right. So these are all things which are possible. Normally, we don't see this. In the normal chemistry, when you are studying chemistry, gas phase chemistry, liquids, solids, you don't see all these. But at the interface, all these things are happening. We need to look at them. So what is important is adsorption is the key for all processes. Adsorption is key for all processes occurring at the interface. Okay. Now adsorption, as you know, this is adsorption of the molecule. This, for example, a Y2 molecule, a diatomic molecule, is actually approaching the surface. This is the surface. It is approaching the surface. As it approaches, it falls into a trap, physically absorbed trap. This is a potential energy diagram. This is a potential energy, right? So the molecule gets trapped in the potential energy on the surface, which is basically physisorbed. In the sense, the potential well is not deep. So it is initially the molecule gets trapped in the potential energy well as a physisorbed molecule. So here, what a physisorbed molecule means what? It's a molecule which does not undergo any dissociation or any change in electronic structure. It's a molecule which just going and sitting on the surface. Nothing happens to this to the molecule. Nothing happens to the molecule. It's just only interaction is due to through van der Waals interaction. Van der Waals interactions are there even in gas phases, right? Gas molecules have to interact because of the van der Waals forces. Nothing happens to the molecules. So it's a physisorbed molecule. It is sitting in the physisorbed well. But then this molecule, which is now sitting on the surface, can actually cross this barrier and come to chemsorption well. But it has a small amount of activation. So this is a zero. This line is a zero potential. So it has to go little above to cross this point and come to the chemsorption well. So there are cases where the molecules first go and sit in the fizzable molecule and then slowly cross that barrier and then come to the chemsorption well. But once it is in the chemsorption, you can see this is very deep. The energy is energetically very stable compared to this is energetically stable. Right? If you want to dissolve, you can just give a small amount of heat energy, this will go away. Or this can actually come cross this barrier and come here. Whereas for this, you can see here, if you want to dissolve this one, you need a lot more energy. You need a lot more energy, and then it is very close to the surface. This is ZC, whereas this is ZP. The distance between this one, the minimum of the potential energy well with respect to the surface is large. That means its distance is more. Okay, molecule to surface distance is more in the case of dissolved molecule, whereas the chemsorption molecule is much closer, and then there could be some interaction, stronger interaction in terms of exchanging energy, exchanging electron charge, etc. Okay. Now, so it can happen that this point of cross, what you are seeing here, this need not be above the 0. It can be below also. So in this case, what happens is the molecule gets trapped here, physisorption. Sometimes people call this a precursor state. People call it as precursor state. It's a kind of fizzed state. Okay. Precursor state. So from here, it doesn't have to go all the way to above this. It just only small amount of energy is required. Is enough for the molecule to slide to the chemsorption well. In the previous one, if you see, the molecule has to cross and then give little extra energy. There are delta E, activation energy is required here. But in this case, it need not go above. It just small amount of energy is sufficient for the molecule to slide over from dissolved state to chemsorption state. Now look at here. That means there is no activation barrier. There is no activation barrier. It is well below this 0 value. There is no activation barrier, right? But in cases where there can be activation barrier, which I showed you just now, there is an activation barrier here, EA, for the molecule to jump into the chemsorption well. So activation barrier for chemsorption. Activation barrier for chemsorption. Okay, all right. So all these things are possible depending on what molecule you are talking about, what surface you are looking at. There are lots of variety of surfaces are there. There are so many different molecules. All these are all possibilities. All these are all possibilities. Now, there are some differences here. Physical adsorption, chemsorption. The temperature range. There is a large temperature range where the chemsorption can occur, virtually unlimited. Okay, but given molecule may effectively adsorb only over a small range. For example, oxygen adsorbs very at any temperature. Carbon monoxide, for example, even room temperature it will adsorb, slight high temperature it will adsorb. So any temperature it can adsorb on the surface. For example, on nickel surface or iron surface. Now, however, physisorption happens only below condensation point of the gas. It is physically adsorbing. Condensation means it starts condensing when the molecules come together. Vapor condenses, right? What are the forces involved in that? Kind of van der Waals forces. Right, so it condenses. See, physisorption is also similar to condensation. So physisorption happens at the condensation temperature. At the condensation temperature. Mostly, for example, you take xenon, nitrogen, they start adsorbing less than 100 Kelvin. CO2 at less than 200 Kelvin. Okay, that is basically physisorption, and the molecular structure will not change much. Molecular structure will remain as it, molecule will not get disturbed. Okay. Now, adsorption enthalpy when the molecule adsorption is a exothermic process or endothermic process? Exothermic, endothermic. Adsorption has to be, it has to interact. When it's interacting, the small amount of energy will always come out. Adsorption is always exothermic. Delta H. For example, delta G is equal to delta H minus T delta S. You have this expression. You are aware of this expression? So, when molecule adsorbs, what happens to delta S? Decreases, because it is losing its degrees of freedom, it decreases. So, this will become, this is a positive thing, right. So, this is a negative, this is delta H. This factor for delta G to be negative, this entire expression has to be negative. So, if this has to be negative, the delta H should be more negative, right. So, if delta S is positive, this becomes negative, this term is positive, right, this is negative. So, this has to be, sorry, the delta S is negative here, not positive, delta S is absorbing. So, entropy decreases, this is positive, this is negative. So, this term becomes positive. So, this term should be negative enough to make the delta G negative, then only adsorption will take place, then only adsorption takes place, okay, alright. So, delta H is usually is always negative, if it is physisorption or chemsorption delta H is much more high. Now, here adsorption enthalpy, that is delta H I am talking about, adsorption enthalpy wide range, it varies between 400 to 800 kilojoules per mole for chemsorption, it is quite high, whereas in the case of physisorption it is only about 40 kilojoules per mole, less than 40 kilojoules per mole. And crystallographic specificity is also there. For example, crystallographic specificity means you have this Miller indices 111 plane, 100 plane, 111 plane, etc. So, it also depends on the nature of the plane. Is it 111 plane or 100 plane or any other plane? Depends on the plane also. Depends on the plane. Particularly, if you take for example, if you take these planes, there will be a lot of variation in chemsorption in these cases. It will not be same. It will not be same. Okay. Now, but in the case of physisorption, it does not matter what plane it is going to be same. It is going to be same. Independent of surface atomic geometry. What is the difference in all these planes? The atomic geometry are different. I will come back to that a little later. Atomic geometry is different. How atoms are arranged on those planes are different. So, that really matters if you are talking about chemsorption, but it does not matter when you are talking about physisorption. Okay, all right. Okay. Now, next in nature of adsorption. Very often chemsorption is dissociative or strongly bonded. The adsorbate molecule will form chemsorption bond with the substrate. So, it can be dissociative also, it can be dissociative. But whereas in the physisorption dissociation is possible? No, molecule will remain intact, molecule remains intact, right, it does not change. So, that is the non-dissociative and reversible. Of course, you can remove the molecule can go away from the surface also, it is reversible. Chemsorption also can be reversible, but it can be irreversible also. For example, if it is oxygen goes and sits on a metal surface, forms an oxide, it is irreversible, it already formed an oxide, right, okay. So, it can be irreversible also, in this case. Now, nature of uptake, for example, saturation uptake, chemization generally happens only one monolayer, because the entire surface, once it is covered, that is all over. Interaction is, second layer is above that, so it is not going to interact with the substrate. So, normally it is confined to one layer, whereas in the case of physisorption is condensation. Suppose I take a metallic surface and expose it to water vapor and then leave it there, saturated water vapor, it will form one layer, second layer, third layer. After some time you start seeing the film there, water film, right. Initially you do not see anything, there is one film, one layer, you may not see it, but as it condenses more and more, physisorption, then you start seeing film after some time. With the naked eye you can see that, right, isn't it? Right. So, the multi-layer, that is basically multi-layer is possible in the case of physisorption. And then you have kinetics of adsorption. It is a F1 activated process, as I showed you. It's a very variable, but it is an activated process, whereas in the case of physisorption, it is a non-activated process. It is not activated. As I said, physisorption, the molecule gets trapped immediately in the small well, but in the chemizorption, it just goes into a deeper well. So, it is an activated process. Okay. So, these are major differences. Okay. Now, chemistry on these solid surfaces are the important, particularly in the case of heterogeneous catalysis, electrochemistry, tribology, nanoscience, materials processing. These are some of the examples I gave you, there are many more. Okay. Now, catalysis macroscopic to molecular. Earlier days, people have put some catalyst, reactants and got the products. They do not have much information about what is happening on the surface, how these reactant molecules are interacting and then giving the product. They have very less information, but nowadays the more and more information at molecular level information is coming out. Molecular understanding of how reactions taking place on surfaces or interfaces is available now. Okay. So, you have metals, surfaces, catalysis. So, mostly in catalysis, particularly heterogeneous catalysis, metals play important role. Of course, oxides are also there, sulfides are there, there are many other materials. But if you take metals and then their surfaces are important in catalysis. Now, when you look at the surfaces, for example, as I said, 111, 100, 110 planes, atomic arrangements are different. Okay. And also different, because the atomic arrangements are different, chemical reactivity is also different. Chemical reactivity is nothing but catalytic activity, that is also different. So, if you change the plane, atomic arrangement is different, chemical reactivity is different, catalytic activity is different. But we do not see that. If you have a small fine particles of catalyst, you are not able to see that, but it is actually true, it is happening. Okay, I just want to give you quickly, since we talked about heterogeneous catalysis, if you see somewhere 1800, year 1800, there was nothing much, there is not much known about heterogeneous catalysis, only it was just started for, Davy first started saying that there is a catalysis kind of thing, phenomenon is happening, and Berzelius, all these people were working until 1900, about a century ago, 1.2 centuries ago, suddenly people have started looking at ammonia synthesis. There are few other processes also. Ammonia synthesis was a breakthrough. So, people who are working on several variety of materials finally found out osmium, ruthenium, iron. These are the three which are very active for ammonia synthesis. So, they start this is a place where the catalysis took prominence, and then started a lot of experimental industrial catalysis has started developing here. industries have come up. Once that Haber process is proved, industrial catalysis started taking up. So many industries are there, catalysis industries. And then, but then science of that has not improved. And see here, so then some of you said on Langmuir isotherm, Langmuir started looking into that. What is the reason for catalytic activity, etc. He started looking at Langmuir immediately after that. And then Hinshelwood, transition state theory, all of you are aware of transition state theory. Transition state theory also started contributing here. And then spectroscopy started coming to picture here somewhere around 1950. Somewhere here. IR spectroscopy. And then surface chemistry started coming in 1970s. And then computational chemistry started contributing to that. And then there are several Nobel Prizes. Latest recent one is Aptel 2007. He received Nobel Prize in catalysis. So nowadays, so you can see industrial catalysis is taking off very fast, and then the understanding of catalysis is a little slow compared to this is very slow. But now in situ spectroscopy technique, operando techniques are being used to study catalytic surfaces. This is an area which is very important currently for to understand or to develop new catalysts and new catalytic processes. A lot of research is going on in this area. Okay. So these are the gentlemen who did all that. Fitzhaber, Bosch, Nobel Prize, both of them received Nobel Prize somewhere around in this region. Langmuir received Nobel Prize in 1932. Aptel, this is the person who received Nobel Prize in 2007. Okay. So that is just a story of catalysis, how it has developed, just to give you an idea of what it is. So current focus is the structure of the catalyst, activity and active spectacular surface species, spectator surface species, finding out what species is important, what is spectator, what is actually getting involved in the catalytic processes. For that you have to use in situ methods, operando methods, computational methods, selectivity, chiral surfaces. Now people are talking about chiral surfaces to design chiral molecules. And then stability and durability. Catalyst has to be stable for a long time, otherwise industries will not accept that. So these are some of the points which people are looking at. See, if any one of you is interested in computational chemistry, computational catalysis, theoretical, if you are interested, I would suggest you read this computational design of catalysts with experimental validation. Okay, there are faculty in our department who are working in this area, and also many other places. Professor Annaberson must have given you some idea of what are the institutions available, what's going on. Huh? Okay, all right. So everybody need not do experiments. Some of you can do computational also. Computational chemistry is also important in this area. Computational catalysis. So don't worry whether you understand or not is a different thing. Go read it. Start reading. Even if you don't understand, read second time, read third time. It will, right? Okay. Okay. So let's go to the next slide. Shall I move on? Okay, some of you are noting it down. Do you have access to the journals? You write to Professor Annaberson, he will send it to you, or you write to me. I will send the journal papers to you. Okay? All right? Don't hesitate, ask. Don't hesitate. I want this, I want to do this. Ask. No problem, nothing wrong in that. Okay? All right? Yeah. So now, since we are talking about catalyst, it's a typical picture of a catalyst material. See, the big thing which you are seeing here is a support. Support is usually aluminum oxide or silicon, SiO2, Al2O3, etc. Right? On that, these small dots, these small particles here, these are all catalytic particles. They can be platinum, can be palladium. These are the particles. See, they are sitting on that. Why? So why do we need to this one support for these particles? For example, this support can be spherical or it can be cube, can be faceted surface and things like that. So this is the basically support, oxide support, and these are the metal particles which you are seeing here. This is the actual catalyst particle taken picture, SEM picture of the catalyst particle. This one, right? So why do you think we need this support for these particles to sit? Without this, you can use this particle directly as a catalyst. Because these particles adhere to the surface of the support, right? They are sitting like this. If there is no support, they stick to each other, and then they become bigger and bigger, and so smaller particles will coalesce and then start bigger and bigger. They start growing bigger and bigger particles. So they lose the activity. They lose activity. If they are interacting with the support, right, then the interaction between the particles is less, and then the reactivity will sustain for longer time. Okay, you need a support. You need a support. All right. Now, this support, if you see, these are particles of nano size, because everybody talking about nanochemistry, nanotechnology, nanoparticles. Catalyst science is already nanoscience. Long back, people have designed catalysts where the particles are in nano size, right? So modern catalysis is preeminently nanotechnology. We didn't name it as nanotechnology, but it was actually nanotechnology that was used. Okay. Now, if you see some of these particles, these catalytic particles, as I showed you here, these particles, if you see them little closer using a electron microscope, what you see is this kind of particles. These particles have planes here. You see that 110, 111. These particles have planes. They have different shapes, and they will have planes. So if you say draw a bigger spherical particle, big one, you can see here the 111 plane. You are aware of 111 planes? Suppose you take a cubic let us say a cubic system. If you take this as the origin, that is 100 plane. Okay, and then this is 110 plane. Okay. Little difficult. This point, and this point. These 3 points will give you 111 plane. This point, and this point. Whereas this point, and this point, that gives you 110 plane, right? And this point and this point gives you 100 plane. You are able to see that? Right? So, all these planes what you are seeing here, they are all there in the particles, smaller particles. When the particles are very small, these particles expose themselves in different planes. Okay? This is known. For example, look at this one, this particular figure. This is a scanning electron microscope, micrograph of palladium nanoparticles. You see, these are all, if you see this one 50 nanometer size particle, you see the shape. It has this shape of, for example, something like one of these shapes, right? There are different shapes. So, this is the shape. Okay. Now, these small particles will have all these planes. Some of the planes are more prominent, some of the planes are not prominent. So, now when these planes are formed, for example, in this case, when these planes are formed, some of these planes can be very active, catalytically very active. Some of them may not be active. So, that is where comes the selectivity or selectivity of the reaction. A reaction can take place more selectively on a particular plane, These are not easy to study unless you have surface chemistry, surface techniques. So, as I said, so all these particles will have for example, if you look at a bigger picture, you can have a particle which contains different layers of atoms. You can see there is a vacancy here, this is a step, atomic step, and then there is a vacancy, this step is discontinued here. Atomic step vacancy, and there is a step here, this is a step, and these are surface clusters sitting on the surface, and there is a kink here, that is kink means at the corner, right. So, all these are possible on this particle that you are seeing you are seeing here. That is the reason why these particles are very reactive. All these points are very reactive spots, and then you make smaller and smaller particles, you will actually enrich them with all these defects, and then the particles become reactive, and then you have to stabilize these particles to get the good reactivity. Okay. Yeah, so one example I just this is a different example. For example, I have white tin which has a unit cell like this. This is a kind of a BCC unit cell, right? And then you cool this to 13.2 degrees centigrade. You get gray tin. Unit cell is different. Unit cell is different, right? See that? Take this one, white tin, and then cool it to less than 13.2 degrees centigrade, and leave it for some time. It will break into pieces. It will break into pieces because the crystal structure has changed. That it induces a strain, so it breaks into pieces. So, these are more stable. This is more stable at less than 13.2 degrees centigrade, and this is more stable above 13.2 degrees centigrade. Okay. Similarly, our particles also, these catalytic particles, their stability is very important. At what temperature they are stable, what planes have to be there for the particles to be stable, right? Those are all very important in catalytic activity. So, these are interesting things. Again, nanoparticles. Here there is a glass here, there is a cup. This is called a Lycurgus cup. It is displaying two different colors here. In the daylight, it shows green, whereas if you shine the light, above this through this cup here, it shows red. Color has changed. So, what is the reason? What is inside this? This cup contains small nanoparticles of gold and silver in the ratio of 14:1. Small nanoparticles of gold and silver are in this glass. So, those are responsible for change in color. Have you heard of, how many of you have seen this cup? Some of you have seen it. So everybody should see that. You see that? It changes the color. Changes the color. Okay. So these people have done this. Some of these things are there in India also, but we have not seen it carefully. People have done the similar things in India as well. Now coming to these planes, which we have been talking about, planes 111, 100, etc. For example, if you see, this is the FCC unit cell. You know FCC arrangement, right? ABC, ABC, ABC arrangement, right? So there, if you take this plane, so 100 plane, this is 100 plane. Here, this is 100 plane. This is 100 plane. So this is 100 plane. Now you extend it in all directions, right? Then you get this kind of atomic arrangement on the surface. Do you see that? This is square geometry. You take this one, extend it in all directions, you should get a square geometric network like this. These are all atoms which are on the surface, which are atoms on the surface. What is the coordination number of this atom which is sitting on the top? It is not 4. There are some atoms below, they are also touching. Only on the surface plane there are 4. So 1, 2, 3, 4. 1, 2, 3, 4. But this light blue atoms, they are below, they are also touching. You have to count them as well. Yeah, 8. Whereas same FCC in the bulk, what is the coordination number? The same atom is sitting in the bulk. So you have a 4 below and 4 on this plane, on the top another 4 will be there. Total 12. Coordination number 12. So bulk atom has 12 coordination number, it is very satisfied, right? Whereas surface atom has coordination number of only 8, and this is not satisfied. So this is unsaturated. So that is active. It wants one more bond to be, 4 more bonds to be formed, right? So that is this plane. Now look at this FCC 110 plane. 110 plane is now this one, and this one. This one, right? Now remember, this is the 100 plane, right? These atoms are touching. And now this is actually face centered. Since it is a face centered, there should be one more atom here. I have not put it here. There should be one more here. Every face has one atom. That is not shown here. There will be one atom here, one atom here, one atom here, and then one atom here, right? One more should be there. This is a face centered cubic. Every face has one atom at the center, right? Now these atoms, this face centered, this is the one which is touching. You see here, these are touching, whereas this is not touching. So you just have to take this one and then turn it 45 degrees, extend the the mesh so that you get this one. Are you able to see that or not? Take this one, keep on adding, and then you turn this by 45 degrees. So you get this mesh. Similarly, you take this again. Now you consider this plane from here to here, this plane, right? This plane is touching. That is this plane you are talking about. So you will have course, I am not drawing the central atom here. Okay. This is the plane. This is 100 plane, 110 plane. This plane. Okay. That plane, if you see how atoms are arranged, you will see atoms are arranged in this fashion. So there is one row of atoms, another row of atoms, third row of atoms, so on and so forth. Each row there is a gap between the two rows. There is a gap between the two rows. Right. So that is so this atomic arrangement is different compared to 100. Now you go to 111. 111 is here. This one, and this one. These three corners. You try to connect them. What you get is a hexagonal arrangement here. This is hexagonal arrangement. See, each atom is surrounded by how many? 6 atoms. So hexagonal arrangement. So the atomic arrangements are totally different depending on the surface plane you are looking at. Crystal is same, FCC crystal, but different planes have different atomic arrangements. Different planes have different atomic arrangements. Similarly, you can try even BCC, body centered cubic. Body centered cubic, if you take, you will have 100 plane has this kind of a arrangement, and 110 has this kind of arrangement, and 111 has this kind of arrangement. It's a little complicated, but you can draw them. You can draw them. Now here, what is the coordination number is also different here. You see, this coordination number here is 6 plus 3, 9. See, each one has 1, 2, how many are there? 6 on the top, and below? There are atoms below. Yeah. So the coordination number is 9. So here it is a little difficult, but this coordination number is also different. So the coordination numbers are different, atomic arrangements are different on these planes, even though the crystal, the unit cell is same. Unit cell is same. So accordingly, the reactivity will be different. Similarly, you can also write hexagonal plane. For example, hexagonal HCP unit cells. If you take here, if you take this particular plane, all of them are hexagonal plane. So this is similar to what you are seeing here. 111 FCC is same as 111 H001 of the HCP. These two are similar. This one and this one. Okay, right? So the reason why I am showing all this one is that these planes are different, atomic arrangements are different, reactivity is different, and if some of these planes are active, I will show you one example here. Before I go to that, I wanted to show you, this is the plane. Yeah, whatever I have drawn, I have shown here. FCC lattice here. 100 is this one. If you take one of these as a origin, you can take 100 plane. What I have drawn here is given here, and 110 plane, this one, and this is 111 plane. This is a 111 plane. These are the planes. If you see, A is a lattice constant. If you take A as a lattice constant, if you take this plane, and then this is the image of that. So A, and this is the image of the this plane. So this is A, this is A, and then this is root 2A. Whereas in this case, if you take this plane, one side is root 3 by 2A and root times A. So you have to do this geometry a little bit. Okay, can you do that? You draw these 3 for an FCC unit cell and see whether what is given here is correct or not. What is this length here from here to here? That is lattice constant, right? A. This is A. This is also A. That's what is shown here. A. Of course, this is should have been drawn little longer, because by length this is not equal to this. You have to stretch the figure little bit. This is A, and this one, if you see, all the three atoms are touching. So all the three atoms are touching. This is a diagonal part of that, and this one is this part. These two are not touching. They don't touch. So this is A. Then this should become root 2A. Right. In this case, this is diagonal part of that, root 2A. So you have to find out what this value is. So root 2A and root 3 by 2A. Okay. You draw that figure, and then go back and do a little bit of geometry. You will be able to figure it out.
SwayamPrabha. Digital India. Educated India.